Hello, in this video, let's look at the frequency response of circuits which have inductors and capacitors. So first thing we know is if you think about capacitors, inductors and resistors, they are what are known as linear elements. Right? And when I say linear elements, I mean that the relationship between current and voltage in these elements have a linear function. That is, if the current changes by 2x, then the voltage is going to change by 2x, right? So when we look at frequency response, what we are trying to understand is what happens to these systems as we apply time varying signals, right? So in addition, what we want to do is we want to think about a system made up of RLCs, and I want to apply a time varying input and I want to see or estimate what the time varying output of that signal is going to be. Now, an important signal that we normally look at when we are doing these studies is the sinusoidal signal, right? That is, we can apply a sinusoidal voltage, and because it's a linear system, the output is also going to be sinusoidal with the same frequency. Now, that is the beauty of the sine and the cosine functions, is that both the sine and cosine functions, when you differentiate or integrate them, you get back the sine and cosine, right? Sine and cosine are only separated by a phase difference of pi by 2. Suppose I have an input signal which is V in sine omega t, right? So let's assume that it's a sinusoidal signal with a frequency of omega. Then I know my output signal is going to be of the form V out sine omega t plus phi, right? So the frequency at the output is the same as that of the input, right? What differs is the magnitude, and in the most generic case, it's possible that a phase might be attached to the signal. That is, both the input and the output signals may be out of phase. So when we want to define this system, we talk about two parameters, right? One is known as the gain or the amplitude gain of the system, which is nothing but V out upon V in. Now what you need to know is that this function is a frequency dependent, right? In the sense that the gain is going to depend on the frequency of the signal. And so sometimes this is shown as the modulus of t, and that is given by V out by Vn. And this t stands for the transfer function, right? And as we have seen in transistors, etc., transfer function basically relates the output of the system to the input of the system. And the other parameter, so this would be a function of omega, and what you see is that you introduce a phase, so let's call that angle t, which is equal to phi, and this is also going to be a function of omega. So in other words, when I change the frequency of the signal, I'm going to get a change in both its amplitude and its phase. Now a sinusoid, the other advantage of thinking about sinusoids is any time varying signal can be thought of using Fourier series expansion, can be thought of as a linear sum of sinusoids. Therefore, once you understand how a sinusoid works in a linear system, then any signal can be decomposed into sinusoids and then look at the system response for every sinusoid and then build up the output signal, right? So knowing how a sinusoidal response is of a system gives you all the information needed to understand the system. To do this, we need to do some sort of algebraic manipulation, right? So if I'm given a circuit, I need to understand how do I pull out the gain of the system and how do I pull out the phase of the system. So to do that, we use a parameter which is a complex frequency variable, and this is denoted by the letter S, small s, right? And so what happens is, in terms of S, the impedance of an inductor is given by S into L, where L is the inductance of the inductor, and similarly the impedance of a capacitor is given by 1 by SC, where C is the capacitance. Resistance is not a function of frequency, so resistance continues to be the same as R. So basically what we would do to find the transfer function of a circuit is replace all inductors and capacitors with their impedances, right, in terms of S, and then use our circuit analysis rules to find the transfer function in the S domain. And this is known as T of S, and it's given by V out of S by Vi of S. Right? So what we do is we solve the circuit to get a transfer function in the S domain. Now to bring this back into the physical realm, we need to now connect this S to a physical frequency. What we do is we replace S with j omega, where j is the complex square root of -1. Transfer function then can be written as T of j omega, which is then given by V naught by Vi. And this term basically has a real component and an imaginary component. So I can talk about the amplitude of T of j omega, which is the amplitude gain of the signal. And since it's a function of omega, you directly get the response as a function of omega. And then we talk about the phase of this complex number, and that's going to be the phase response of the system. So any circuit, once you replace the reactive elements with their impedances in the S domain, solve for the output voltage as a function of input voltage, or output current as a function of input voltage or current, whatever you have it. And then once you get that, replace the S with j omega, where omega is the physical frequency of the signal. We are talking about single time constant circuits known as STC circuits. So a single time constant circuit can be thought of either as a low pass or a high pass circuit. What I mean by that is, a low pass circuit allows signals of very low frequency to pass through. So low frequency signals pass through and high frequency signals get attenuated. Now what is a high and what is a low frequency is going to depend on the time constant of the system. So we'll look at that in a little bit detail later. In contrast, the high pass circuit is going to allow high frequency signals to pass through, and it's going to attenuate the low frequency signals. Broadly, you can think of any single time constant system as either a high pass or a low pass circuit. Now, how do you identify these? Right. So one simple way to do it is remember what a capacitor or inductor does at low frequency. So if you think about a capacitor, right, when omega is equal to 0, that is when I have DC voltage, the cap is an open circuit. And when omega tends to infinity, the capacitor becomes a short circuit. Similarly, an inductor, when I apply a DC current or voltage to the inductor is a short circuit, right, because there is no magnetic field built in. And when the frequency of the signal tends to infinity, then my inductor becomes an open circuit. So to identify whether a circuit is a low pass or a high pass system, one quick way to do it is set omega equal to 0 and then see if T of omega equal to 0, that is the transfer function or the gain of the signal when I apply a DC voltage at the input, does the gain go to 0 or does the gain remain some fixed quantity? So if the gain of the circuit goes to 0, so what we see is that a DC value does not pass through the system, which means that this is a high pass circuit. On the other hand, suppose I select omega as infinity and look at the function as omega tends to infinity. If the gain for such a circuit goes to 0 at infinity, that means that it is attenuating high frequency signals. So this would be a low pass circuit. So we can look at some of the examples of low pass circuits. So the simple low pass circuit, and you can change between low pass and high pass very easily. So let's think about it. The simplest low pass circuit I can think of would be something like this, where I apply voltage here and I measure the voltage output here. So now if you look at this circuit, right, when omega tends to infinity, this capacitor gets shorted, and which means your V naught is going to go to 0. So this circuit, as omega becomes higher and higher, the output voltage goes to 0. So this would be a low pass circuit. On the other hand, if I set up a circuit like this where I interchange the resistor and the capacitor, in that case what's going to happen is, at low frequency, that is when omega is equal to 0, this capacitance is an open circuit. And so this means that your V0 is essentially 0 because there is no power coming to that signal. And when omega tends to infinity, right, the capacitor becomes a short, and that allows your V0 to follow Vi. So this is the case of a high pass circuit, right? So by playing around with where R and C, or where you're pulling out the output voltage, you can either make the circuit look like a low pass filter, or a low pass circuit, or a high pass circuit. Let's look at another example. Let's think about a circuit which does this. So this is L, this is R. Now this circuit is, again, let's think about it. When omega is 0, this inductor is a short, and so output voltage follows the input voltage. So it allows a DC signal to go through. However, when omega tends to infinity, this inductor becomes an open circuit. It has a very high impedance, and at that point V0 is equal to 0. So this would be a low pass circuit. Now I can think about a case where the output is a current. For example, let's look at a circuit which is this. So let's assume that this is my input signal and my output signal is actually a current I0, right? Now, when my input is a 0, my inductor is a short, and therefore my I will be some value given by Vi upon R, right? Now, however, when omega tends to infinity, my inductor becomes an open circuit, in which case IO, or the output current, goes to 0. So here again I have an output signal that goes to 0 at high frequencies, indicating that this is a low pass circuit. Right, so similarly you can think of similar circuits. Another circuit which I can think of for a low pass circuit would be something of this form. Suppose I take an input current II, this is my R, this is my C, and if I call the current through the resistor as my output current, then this again would be a low pass circuit. Why? Because the capacitance is an open circuit at omega equal to 0, and so all of your II flows through I0. But when your omega tends to infinity, when your omega tends to infinity, this capacitor becomes a short, and so all of your input current goes through the capacitor and the current through the resistor goes to 0. Right? So this is an example of a low pass circuit. So now let's think about the frequency response. So that is, I want to understand, is there a generic method to think about low pass systems or low pass circuits? So let's look at the frequency response of low pass single time constant circuits. So any low pass single time constant circuit can be written of the format T of S is equal to some K divided by 1 plus S by omega naught. Or in other words, if I convert this to a physical frequency, this gives me T of j omega is given by K by 1 plus j omega by omega naught. Now this omega naught is nothing but the reciprocal of the time constant of the circuit. So this is where the time constant comes in, and it is this omega naught which gives you a frame of reference to now identify which signal would be considered a low frequency and which signal will be considered a high frequency. And so that is going to be dictated by the time constant of the circuit. So now if I look at this complex function, then I can talk about its magnitude T of j omega as K divided by square root of 1 plus omega by omega naught the whole square, right? And so this is the amplitude response of the circuit. Similarly, the phase response of the circuit is going to be given by minus tan inverse omega by omega naught, right? And so this is going to be the phase response. So let's see how these functions look like. So if you look at the amplitude response, you see that the amplitude response is related to omega in the denominator. So as your omega tends to infinity, or as this number, so as omega by omega naught, this number keeps increasing, the amplitude response keeps dropping, right? So therefore, this ratio of omega by omega naught tells you what would you consider as a high frequency. So if you say that the gain drops to say half or say 1/10 of the gain at low frequency, then I'd consider it as a attenuated signal. And so how you'd pick that would depend on the ratio of omega by omega naught. Similarly, if you look at the phase of the function, the phase is given by minus tan inverse of omega by omega naught, right? So when omega is 0, this angle is 0 degrees. And when omega tends to infinity, this angle goes to minus 90 degrees, right? So you see that the function, when the frequency is close to 0, if you give a sinusoidal input, the output is going to remain largely sinusoidal. However, you see that the same output completely becomes out of phase or becomes a cosine signal when you go to very high frequencies, right? So that's the meaning of the phase response of the circuit. Now, we normally plot this using specialized plots known as Bode plots, which plot log of t of j omega versus frequency omega in the log scale, right? So in other words, this is a log plot, and the reason is because this gives us a better way of looking at these functions, because these functions decay pretty quickly. So what we do is, now if you think about t of j omega, right? T of j omega, or the magnitude response of t of j omega, that can be written as k times 1 plus omega by omega naught the whole square under the root. Now when omega is much larger than omega naught, I can approximate this t of j omega as k times omega naught by omega, right? In other words, I see that there is a function that is inversely proportional to the frequency at very high frequencies. So if I plot this on a log scale, I'm going to get a straight line whose value keeps dropping exponentially. So how do we define omega naught in such a system? So now omega naught, let's find the gain at this frequency. So the gain at omega naught is going to be given by modulus of t of j omega at omega equal to omega naught, which is given by k by square root of 1 plus omega naught by omega naught squared, which is k by root 2. So omega naught is defined as, sometimes called as, the cutoff frequency, and it's the point at which the amplitude gain drops to 0.707 of the gain at DC, right? Now, what is this 0.707? Now this, if you now think about it in dB, right? When you think about dB, what are we saying? We're taking 20 log of this gain. So in dB, now dB's unit, it's decibels, and normally it's expressed as 20 log of t of j omega, right? So at omega naught, what we see is that the gain in dB drops by 3 dB, because 20 log of 2 or 10 log 2 basically becomes 3 dB, right? So in other words, this omega naught is also sometimes known as the corner frequency, and it is the frequency at which the gain drops by 3 dB, so sometimes also known as the 3 dB frequency. So now if I plot the amplitude response as a function of omega, so this is in dB, the gain, and I'm plotting this, again both are in the log scale, so basically every position is going to give you one order of magnitude less. Similarly, I can think of this in the following fashion. This can be 1, this is going to be 10, 100, 1000, and this is going to be 0.1. So let's assume that the gain at low frequencies is some value here, right? So at omega equal to omega, so in reality, your function is going to look something of this format. So in reality, your function is going to look like this. This is your omega naught. So this is how the gain would look like. And what we do is, we approximate the gain function to look something like this. It's a straight line till omega naught. Then it is another straight line which drops at minus 20 dB per decade. That is, every increase or every decade increase in frequency, the gain drops by 20 dB. So what we've done is, we have approximated this into a piecewise linear function, where we're saying that at all frequencies less than omega naught, the gain is a constant given by whatever log 20 log k would be, and at higher frequencies it drops linearly from the gain in dB drops linearly over logarithmic frequency. Now this approximation works very well when you're at low frequencies or when you're at high frequencies. The approximation breaks down or induces a lot of error around omega naught, right? So if you're actually looking at the performance of the system around omega naught, you want to be careful. But otherwise, this approximation gives a pretty good handle of what's happening for frequencies much less than omega naught or much greater than omega naught. Now let's also look at what the phase response looks like. So suppose I plot the phase response of this system. Okay, again I'm going to do the same thing. I'm going to plot it using a log scale for the frequency. So again we note that the phase response is given by minus tan inverse of omega by omega naught, right? So the angle is going to be a negative angle. So it starts off at 0. Let's say this is your 90 degrees minus 90. And the halfway point is going to be 45 degrees. Now at omega equal to omega naught, the phase is going to be essentially tan inverse of minus 1, which is basically 45 degrees, right? And then it asymptotically is going to approach 90 at large frequencies. So therefore your phase response is going to look something like this. So the signal changes from being a pure sinusoidal at very low frequencies to actually making a cosine function at high frequencies. So this is typically how the frequency response of a low pass single time constant system is going to look like. Now let's look at the transfer function of a high pass circuit. So a high pass STC circuit can be thought of with a transfer function given as T of S is equal to Ks by S plus omega naught. Or in other words, at physical frequencies, I can write this as T of j omega is equal to K divided by 1 minus j omega naught by omega. And again here omega naught is equal to 1 by tau, where tau is the time constant of the circuit. So again this helps us determine what is a low frequency and what is a high frequency. Now let's look at the amplitude response. The amplitude response of T of j omega therefore is going to be given by K divided by square root of 1 plus omega naught by omega the whole square. So in this case, this denominator tends to infinity at omega equal to 0, right? And so therefore this gain function is 0 at low frequencies and becomes K at high frequencies. And similarly, the angle at j omega is going to be given by tan inverse of omega naught by omega. So here what you see is at omega equal to 0, your modulus of T of j omega or the amplitude gain is 0. And at omega equal to infinity, this gain becomes K, which is then in contrast to the low pass system where it's the opposite. And similarly here if you look at the phase, the phi at omega equal to 0 is actually 90 degrees because it becomes tan inverse of infinity, which is 90, and phi at omega equal to infinity basically goes to 0. So here what you see is that at low frequencies, a sinusoidal signal becomes a cosine signal, and at high frequency, the sinusoidal tends to remain sinusoidal. Right? So now here you see that the amplitude function is an increasing function with omega, right? And beyond omega naught, it tends to stabilize. Similarly, this is going to be a function which falls from 90 degrees to 0. So using the same analogy as the low pass, if I look at the response on a Bode plot, let's plot both the frequency response and the amplitude response on the same graph. So this is 1, or this is 0.1, this is 1, 10, 100. Right? So this point is omega naught. Now let's look at the phase response. So the phase response, if I plot the actual phase response, it's going to look something like this. Again, I'm talking about the gain in dB. So it's 20 log of modulus of T of j omega. So you see that the gain, again, the way the Bode is going to work is the Bode is going to approximate this as a piecewise function around omega naught, right? And if you look at the phase response goes from 90 degrees to 0 through the 45 at the cutoff frequency. And so you have a response which is going to look something like this. So the signal starts off being a cosine function at low frequencies and becomes sinusoidal at high frequency. Both the low pass and high pass systems work in opposite fashions, which is what is expected given the transfer function of these circuits. Now let's relate this to the time response, or the response for voltages changing as a function of time, or input variables changing as a function of time, for a couple of examples. So we've already looked at the step response. So we know that if I take a step response, the step response is going to be given. So if I have an input signal whose input goes from, say, some value 0 to some value x, right? So I have a step at time equal to 0. Then I can write my output function to be some y of infinity plus y of 0 minus y of infinity e power minus t by tau. And so what you see here is that this y infinity is the final value, or the value to which the function is approaching, or the output is headed to. And y of 0 plus, this should be 0 plus. So y of 0 plus is the value immediately after time t equal to 0. And what you see in this case is that the gap between the value and the final output shrinks exponentially. So in a low pass circuit, what you'd see is your y of t gradually increases towards the final value. So if I look at y of t now, your y of t is going to have a function which does this. So here you see that the output starts off at 0 and rises up to some value s, for example. And so your y of t can be written as s into 1 minus e power minus t by tau. So that's basically what you see, that in a low pass system, your output slowly rises up to whatever your final value is. A high pass system can faithfully transmit high frequencies and attenuates low frequencies. So when you look at a input which looks something like this, there are a lot of high frequencies associated with this part of the signal, but at this part of the signal there is essentially no dependence of time. So what we expect therefore is that when the input is a DC value, that is when it doesn't change as a function of time, the output should go back to 0. The output goes high only when there is a change in the input. So the high pass system typically looks like a differentiator in the sense that it highlights changes in the input. So therefore the output is going to look something of this format, where the output is 0. When there is this sharp change of the input, the output goes high, and then the output again drops to 0, right? So what you see is that the output has the form some s e power minus t by tau, and this value of s is going to be dependent on the system. So difference between a low pass and a high pass circuit is that a low pass circuit takes some time to respond to a step input, right? So it induces a delay, right? It is slow to change because of the fact that it attenuates high frequency signals. A high pass system on the other hand, is going to highlight the steep changes in the input and going to attenuate to 0 when the input does not change. And hence what you see is kind of a differentiator like characteristic at the output. Now let's think about a pulse response. So let's assume that instead of a step, I've given a pulse response to the system. That is, my input looks something like this. So at some t equal to some capital T, I bring down the circuit, or I bring down the response to 0. Now again here, this can be thought of as two step functions, right? You have a positive step function at time t equal to 0, and you have a negative step function at time t equal to t, right? Now if you look at the low pass response of this kind of for this kind of an input, what you'd see is that the low pass response is going to look something like this. Once the low pass system sees this increase at the input, it is going to try and catch up, right? And the speed at which it tries and catches up to the input is going to depend on the time constant of the circuit, right? So let's assume that we have a relatively small time constant, which means that it catches up by the time the signal has stabilized. Now, when it sees the second drop in the input again, what is the output going to look? Now output is again going to catch up to the input, so it's going to have an exponential decrease, right? And this is going to be dependent on tau. The rise and fall of the output signal is going to depend on tau, right? And so now if I have a system which has a very long tau, that is, if tau is very large, then it is possible that my input does or my output does not even rise up to its full value. Instead, it starts to fall because of the fact that the input has already been removed, right? So if you look at the response of the for a pulse, right, the response of the pulse really depends on what is t and how does it compare to the time constant of the circuit, right? In the case when the pulse is much larger than the time constant, you will see that the output is going to faithfully respond to the input. However, if t is much larger, smaller than tau, that is, if the input changes faster than the time constant of the circuit, then you're going to see that the output is going to have a hard time responding to the input, right? So this tau is a measure of how long does it take for that particular system to respond to a change in the input, right? So it's a measure of the speed of the system to first order. Now let's look at what happens if I send the same signal to a high pass. So when I look at a high pass system, again remember the high pass system is going to respond to the changes in the input. So what's going to happen is, if you look at the input signal, I see that the input signal rises up sharply here and drops sharply here. Again, a high pass system is not going to respond in these regions when the input is flat. So what you're going to see therefore is, for the high pass system, you're going to see the input spike up and fall, and as long as the tau is small enough, the input is going to spike down and fall, right? So this is the rising edge of x of t, this is the falling edge of x of t. Now again, this is when t is much larger than tau, that is, the system can respond. You have enough time before the signal changes, hence the system can respond to the signal. However, if now in this case again, if my t becomes of the order of magnitude of tau, then what is going to happen is, if I look at my output for a high pass system, my high pass system is going to start to drop, but even before it's able to get to its full value, I'm going to see it come down and do this, right? So what's going to happen therefore is, in this system, you see that the output is not completely discharged, right? Again here, how the change in the signal relates to the time constant of the circuit really sets how the output is going to function. This is again very similar to the frequency response, because in the frequency response too, we had omega naught, and that kind of helped us decide what a low frequency or a high frequency is for that particular system, and that would tell us if it's an attenuated signal or if it's a signal that passes through in the system without any change to its amplitude.